instruction that you're using may no longer be available. It's definitely not Turing complete because it's a whole lot of work. And ROP you can compile to from a high-level language. Bisq, the highest level thing you can do is write macros, but makes it workable. And so to keep it simple, we don't need a full compiler, just an assembler, and that's basically all I wrote. Because for the exploit developer, x86 assembly is not scary, and it shouldn't be. If you find x86 assembly scary, perhaps you shouldn't be writing exploits because that's what it takes. And we only need to support a subset of x86. We don't need to support all the esoteric instructions. We only need kind of the core, some core, like even 12 instructions that we can use. And so we can write programs using a familiar syntax, and the assembler will scan the libraries you give it to just try and make it happen. Again, no support for conditionals or loops. So here's kind of if you can read this, an example of a small scanner that you give it a DLL, and it'll print out the available instructions that you can use for your Bisq programs. Some ones I want to point out, this one right here, move EAX, ECX, that we can use that to read memory. Oh, sorry, first I should point out, you see all the pops over here? Those let us set registers to arbitrary values. Very important. You need at least a few of those, otherwise you're not going to get anywhere. If we have a move ECX into EAX, that's our memory read. We can set ECX, we can read from ECX, we can now read memory. We also have plenty of writes and a couple other useful things. So basically that's enough to write useful Bisq programs. Now to wrap your head around how this works is the programming model kind of takes a little bit to get used to, because when you think about very literally how the stack works, the stack grows downward but unwinds upward. And we're going to write our return-oriented, borrowed instruction programs downward. So it kind of flipped. Basically, you can see in the picture in our code on the right, there's ret 1, 2, 3, 4, but those are upside down on the left because they're being unwound in that order. And so each identified instruction is a word in your vocabulary. So while having a larger vocabulary makes it easier to get your point across in a more concise and more precise way, it's not necessary to communicate. So basically, if you look at how this works, you have to work with the instruction, the vocabulary that you have to get the point across. Like on the right, it'd be nice to be able to just add 3 to the memory pointed to by ECX. But you probably won't find that instruction. So you just need to execute the 5 instructions on the left, which will perform the equivalent operation. So it does take a little problem solving and creativity. Here's how my Bisq programs look. They're an array of strings and values. A string is an instruction that gets replaced with the location in memory of that instruction, and a value is a literal that gets put right into the stack. And you can also make your arrays nested. So basically, what'll happen is it'll flatten the array and then it'll interpret it. So that allows you to write macros, because you can write a small function in Ruby that'll return just an array. And so you can kind of compose these, you can nest these, so it can be an arbitrarily nested array, which lets you have macros that use other macros, and so on. So here's a kind of a quick example of what a small program looks like. I have the macro called clear, which again uses some creative kind of backflips to clear. You give it a pointer and it clears that value that's pointed to by doing some crazy stuff, by setting it, by ORing it with FFFFF and then adding 1 to it, because well those are the pieces that we had, so I had to do you need to use what you have to achieve your goals. And basically the main code is just this function main down here, which just calls clear on a variable that was allocated. There's an allocate function that will allocate you some dedicated memory so you can use for variable storage. And that's basically, I just run this and that'll spit out, like I run it with a list of a DLL, and it will generate this Bisq program for that DLL. So assuming that DLL is loaded in memory at a fixed location, or I can say, load it, generate it with this DLL at this specific location. So if I have a memory address disclosure, I can then just rerun this and generate it for that runtime configuration. So you can also, because you have to do these kind of backflips to achieve these simple operations, and if you use a different DLL to target, all those same instructions may not be available. The idea of the Bisq macros is that you can treat them as virtual methods. So you can basically write your clear function, your set function, and so on, so that you basically write your payloads in terms of those macros, and then when you target a different DLL, you basically just need to re-implement your macros instead of re-implementing your payload, which is much easier. And sorry, Bisq is not available. There already is. Sorry, yes? You're free to do whatever you want. I'm presenting here, so my personal opinion is I think releasing code like this would only help malware. So I personally don't want to do it. For people who do want to try their hand at this, Alex Soderhoff and I give a training called Assured Exploitation. We did it at CanSec West this year. We'll probably do it at CanSec West next year, where we give students a individual license for this software, and then we teach people how to play with it, and they can write their own exploits with it. Wow, I really went very fast. So return-oriented programming can be applied in other fields. Most notably, where you need it is the iPhone. So the iPhone has a code signing enforcement policy, which is basically the biggest security strength of the platform, meaning that you can't inject new code. If you try and jump into, they have NX, so you can't jump into the heap where you've injected your shellcode. You can try and jump into mprotect and make new memory executable, but the kernel will deny it because that memory has not been signed. You can try and change memory, change code that's already loaded, but if you make it writable, then change it, and then try and make it executable again, the kernel will deny it because you have set the dirty bit and the signature has been invalidated. It won't let it happen. One thing to keep in mind, the reason most people don't talk about this is because they do all their testing on jailbroken phones, and the first thing jailbreaking does is it disables code signing. So that's how you can run unauthorized apps, because the code signing enforcement means that the only code that will be executed by the processor on your iPhone is code that has been signed by Apple and blessed in some weird, pagan ceremony with Steve Jobs present in holy robes. And that's largely a security strength of the platform. And so also be aware that if you're jailbreaking your phone, you are making it 1,000 times easier for an exploit to work on that phone. So, I hope that game was worth it. For instance, at Pwn to Own this year at CanSec West, Ralph Philippe Weinman and Vincenzo Iozzo, who unfortunately couldn't make it here because of the crazy ash cloud, they demonstrated, they won the Pwn to Own for the iPhone with a fully return-oriented payload. So basically, it wasn't a payload stage like I've demonstrated. It used fully return-oriented programming to read the SMS database and send it over the network, which I guess I wouldn't think that the SMS database should be available to all applications, but it's allowed by the sandbox. So they didn't actually have to go and break out of the sandbox to win. Another useful application of return-oriented exploitation is on embedded systems. Embedded systems very often have separate instruction and data caches, and this causes a lot of headaches for exploitation, because if you're trying to inject new code, that's going to be data, and that's going to be in the data cache. And so if you try and point the processor at those memory locations, it's going to get the memory, it's trying to execute code directly from memory or from the instruction cache, which it'll be desynchronized. It won't have the same information as in the data cache. So you'll find this on PowerPC, you'll find this on ARM. I can't remember if MIPS, I don't think MIPS has it. So that's another useful place. The way that I do these techniques is actually most similar to Sebastian Kramer's borrowed code chunks technique. This was like a draft paper that he kind of just put on the web that didn't really receive anywhere near the amount of attention that it should have. And this, this predates return-oriented programming.